Okay, this is to look at infrared spectroscopy. Spectroscopy, like microscope, telescope, uses light, and it's using a range of light. So these are the slides. So when you get the PowerPoint, you can flick through and look at what you want to. The slides that have got a green background, you could take notes from, and the slides that have got a yellow background are a bit of practice. So this analysis that we're looking at, qualitative, remember, is looking at which chemical. So we've looked at mass spec so far, and this is IR. So these techniques will help us work out what chemical we've got. And quantitative, there's a couple of techniques that we'll look at telling you how much. So infrared, NMR, and mass spec, and chromatography we can use to work out what chemical we've got. And chromatography and volumetric analysis are two techniques to work out how much of a chemical you've got. So spectroscopy, scopy, is looking at light. So we have a whole lot of different sorts of light. We can only see one type of light. They have different frequencies or wavelengths. The longer wavelengths have less energy and the shorter wavelengths have more energy. So the particular sort of light that we use for infrared is longer than what we can see, and it makes whole molecules vibrate and move and jump around. If it gets even longer, it's going to affect the nucleus, the protons and neutrons, and we're going to look at this later, radio waves. And we should have done in year 11. Last year we didn't do it, but we did it with flame tests that visible light and UV light has more energy, and it can make electrons jump to their next shell, and then they'll give off that amount of energy as a particular color of light.
Infrared spectrometry helps chemists to identify the functional groups present in a compound. It can therefore help in finding the structure of a compound. A pair of atoms joined by a covalent bond can be thought of as being like balls on the end of a vibrating spring. The bond can vibrate with different amounts of energy at a frequency that depends on the masses of the atoms and the strength of the bond. Lighter atoms give higher frequencies. Heavier atoms move more slowly and so give lower frequencies. Stronger bonds give higher frequencies, and weaker bonds, lower ones. At room temperature, most bonds will vibrate with the lowest possible amount of energy. But if radiation of the right frequency is supplied, the bond can absorb energy and vibrate with greater amplitude. Most bonds absorb energy in the infrared region of the electromagnetic spectrum, which corresponds to heat. Each bond, such as OH, C double bond O, NH, and so on, absorbs at a particular frequency, and this allows it to be identified. For historical reasons, and because the numbers are easy to work with, chemists dealing with IR spectra use units called wave numbers, measured in centimetres to the -1, which are proportional to frequency. All IR instruments have a source of IR radiation. This is a coil of wire surrounded by a ceramic capsule, which is heated electrically so that it gives out IR radiation. In other words, heat over a whole range of frequencies. The IR radiation goes via a series of mirrors into the sample, which is placed here in an appropriate holder, a technique called a Fourier transformation. This gives the intensity of the infrared radiation at each frequency separately. The transformation is handled by the computer and produces a graph of percentage transmission against wave number. This is what the chemist interprets. The essential point is that pulses of infrared radiation consisting of a range of frequencies simultaneously are passed through the sample and arrive at the detector. Some frequencies are absorbed more than others, depending on what bonds are present in the sample.
Okay. So infrared is a lower energy than visible and UV. less energy, so it's longer wavelengths, less energy, and it doesn't promote electrons to higher energy levels. It's used to make the vibration of the molecules vibrate, which is what was on the video. Most molecules will absorb infrared radiation except for symmetrical ones. So these ones we can't analyze with IR. So they need to have a dipole moment, and so these ones don't absorb light. Okay, so it must have an overall dipole to make them move. The spectrums are similar to UV-Vis, which does not really matter. We looked at absorbing of light, not transmitting, to work out how much. We did do that with actually phosphate with our UV-Vis. Light's absorbed, so it's not going to be the y-axis is not going to be the light that's absorbed, it's the light that transfers, moves through. And the x-axis, instead of being the wavelength, so we're looking at a range of wavelengths, but instead of being wavelength, we're going to have 1 over wavelength, which we call the wave number in centimeters to the -1. As the wavelength gets shorter, the wave number, so if this number is smaller, then the wave number will get larger. So wave numbers can be read as waves per centimeter. So the ones up here, the larger the number, the more energy. So this is probably a good one to take. This is green, good one to take some notes of. This is an IR spectrum with a range of wavelengths or wave numbers. The larger the wave number, the shorter the wavelength, and the higher the energy up here. So this, when we look at these, I kind of imagine these as absorbance of light peaks, so upside down peaks. And this is the light from here to here is the light that was transmitted, not absorbed. So if you look at these that way, this is light that's been not absorbed, and then this is the amount of light that was absorbed. So these are kind of upside down peaks. So that's what we refer to them as. We refer to this as a peak, this as a peak, which is kind of weird. You need to recognize when you see, we've got a whole lot of spectra, you need to recognize when you see one that this is an IR spectra. So if you see wave number down the bottom and transmittance on the side, it's IR that we're studying. We're going to look at these, each of these, which bonds absorb more energy. So strong bonds like triple bonds, or it's making the molecule flap around. So if you've got a really light molecule, it'll absorb, strangely enough, a light atom. It'll absorb more energy and wave about. Not that all of this matters that much. Okay, so what we are looking at are our functional groups. So there's only a few, really. The hydroxyl group, the carboxyl group, which we'll have 2 different peaks for, the amine group, and the carbonyl. So we've got carbonyl, hydroxyl, and amine, and these ones we don't really use. And there's also the double bond. I need to put that on here too. Okay, so you need to use your data booklets. So if you get your data booklet, these numbers we have to quote, and we have to quote the whole range. So you'll see that we've got 1, 2, 3, 4, 5 different carbonyl peaks, which will be at slightly different numbers depending on what type of carbonyl they are. And we've got 2 hydroxyl peaks, which are at different numbers depending on whether it's a hydroxyl as part of a carboxyl or whether it's an alcohol all by itself. Okay, So we need to be aware that these will be at slightly different wave numbers. When we're looking at a spectrum, it's generally above 1400 centimeters to -1 wave number that we're looking at for functional groups. Anything below that we call fingerprint region. So anything below kind of the 1400, everything down here, it's a bit of a mess generally, and it's distinctive for an individual molecule. Whereas these numbers, this peak here is for a particular functional group, and this is the OH hydroxyl functional group. So if you've got an OH and that's the only functional group you got, then you are an alcohol. But there are a whole lot of different alcohols. So all alcohols will have this functional group, but they'll have a different fingerprint region. So you can tell if it's a different sort of alcohol. These divisions are a bit weird, so just be careful when you're reading it. They don't go up. So it's 500, 500, 500, and then all of a sudden it's 1,000. So just keep an eye out when you're trying to work out the number. Okay, this is a green slide here. We need to take some notes. When you see a really strong all the way down, it's absorbing a lot of light, not transmitting very much. We call it a strong peak. If it takes up a lot of wave numbers, so the frequency of light that it's absorbing is across a huge range, we call it a broad peak. So they're kind of the main words. If it's skinny, we can call it a sharp or narrow peak, but generally, we're just distinguishing and saying broad. Yep, so we have to quote the specific range, the whole thing. And we're going to look at acids and alcohols, this hydroxyl peak. The acid one is slightly lower and the alcohol one is slightly higher. And we also need to look at this because this is around the same. So all hydrocarbons have carbon-hydrogen bonds, and they'll all have a little peak around just a bit less than 3,000. Okay, so here we have got some notes that we need to take. So we're looking at alcohols. All alcohols have a distinct hydroxyl band, and the wave number is 3,200 to 3,600, so quite high up here. And you can see the little peak for the CH. It's a little bit lower than 3,000, and an alcohol and the CH will be separate peaks. Okay, so you must quote the full range, and you also need to write alcohol on the band to distinguish it from the hydroxyl group that you find here. So this OH, if they ask you to label the peak, then you must label here. Or if you put OH here, you would have to draw a line to show that it's this. Or draw a line to CH to show that it's this. Yep. So be really clear. Alcohols also have because it's COOH, they also have this peak down here, but this is kind of in the fingerprint region, so we're not going to be able to distinguish it from all the other peaks that are down there, so we don't worry about it. So we can see, we can't tell it's an ethanol from this, we can just tell it's an alcohol. So if you're asked to an exam question, what type of molecule is this spectrum due to, provide two pieces of evidence. So this spectrum is due to an alcohol, so be very clear, alcohol. There is a broad, so this is quite wide, and we need to use the word broad, band, between 3,200 and 3,600, which is due to the OH group in an alcohol. So we need to look that up and make sure you've got the right numbers. These are higher numbers than the carboxyl group. So just pause it and write that down. Broad band between the 3,200 and 3,600. There is, okay, so the other bit of evidence, we're going to look at the OH group that you get in acids. So that's one bit of evidence. This OH group appears in acids. How do you know it's not an acid? So we're going to look, we don't have this carbonyl peak, C double bonded oxygen. And when we're looking for that, that is normally around 1700. So we're kind of focusing on the around 3000 when we're looking for peaks, and the around 1700. And you need to quote, if you're saying there's no peak, you need to quote where you would be expecting to see a peak. Okay, so the lack of a peak is also evidence. Okay, we've got 2-methylpropantuol from the textbook and ethanol. There's a little ethanol here. Both have the distinct OH peak that's separate from the CH peak at about 3000. There's also this, don't worry about this. You can tell that they're two different alcohols. That's what I was saying before, because the fingerprint region below 1400 is different for each. Alright, so now I was saying we need to distinguish between the OH peak, the hydroxyl peak of an alcohol, and the hydroxyl peak of a carboxylic acid. So you can see that this peak has moved down. It's kind of a bit of an ugly sort of a peak, and it's merged with the CH peak. So it's further down. So the acid's further down and the alcohol's further away. You also notice this really sharp, strong peak here, and you can see this is 2000, this is 1500, it's at 1700. So that's our our carbonyl peak. So these two peaks you get for a carboxylic acid, and not having that one and having that one is what you would get for an alcohol. If you didn't have this at all, then it could be an ester or a ketone or an aldehyde. Okay, so carboxylic acids, as we said, we've got the OH peak further down. Ethanoic acid, so we've got this. So we need to see this drawn out. So structural, this carbonyl, which is part of the carboxyl. The only time that you really break this up into a carbonyl and a hydroxyl and refer to them as separate things is on an IR spectrum. If you're ever talking about the functional group, how it behaves, its viscosity, whatever, you talk about the whole thing. So Edrolo is actually separating them when they're talking about them, and they're saying we're having a dietol-dipole and a hydrogen bond. The whole thing is referring to having a hydrogen bond, really. Particularly if it's with a carboxylic acid and another carboxylic acid, we get a dimer, 2 hydrogen bonds. Okay, so they're the peaks that you need to recognize. So it'd be good to pause this and at least draw a picture of this. How do we answer an exam question? What type of molecule is this spectrum due to? The IR spectrum is due to a carboxylic acid. Two pieces of evidence. There is a broad, covering a wide range of frequencies, broad band between, and we need to quote the OH numbers for acids. So you need to look up your data booklet and make sure you've got the right numbers, which could be due to the OH group in an acid. There is also a sharp band, and then when you need to quote the numbers for carboxylic acid, the carbonyl in a carboxylic acid. So there's a sharp band here. So you've got the two things. So that's how you would quote it. Okay, so esters, aldehydes, or ketones have just got this. This is an ester. So this is the particular one around 1700. What type of molecule is cis spectrum 2? Provide two pieces of evidence. It could be due to an ester, aldehyde, or ketone because they all have a carbonyl, as there is an absorption band at around 1700. So I've got around 1700. I'm not quoting exact numbers because we can't see, and those peaks overlap for these. So if you can't pick one of them, then you just say that you've got a carbonyl peak at around 1700. There was probably be some other, other spectrum or other information that would make you think that it was either an ester or an aldehyde or a ketone. So there could be something to say that this molecule, when it underwent oxidation, turned into a carboxylic acid, or some other kind of information. So we know also that it's not a carboxylic acid because there is no broad peak or broad band around 3000. So it doesn't have an OH group, and we're going to look in a minute. So we've kind of forgotten these for the second. This peak here, the big one, is generally an OH, but we're just about to look, it could be an NH group as well. Okay, so identifying the molecule. What are the isomers of C3H6O2? And I've managed to draw 9 of them. So I would strongly recommend that you pause the video here and try and draw some. 3 of them have a single functional group. 3 of them have 2 functional groups, and we're not going to name these this year. The functional groups must be the type that we don't name. And 3 of them have 3 functional groups. So this might have been done a while ago. Maybe we do name them. I'll have a little look. Okay, so pause it. I'm going to the next slide. Okay, so we've got propanoic acid. Oh, I've been a bit slack when I've been doing this, haven't I? Didn't put my hydrogens on. That's very bad of me. We've got a carboxylic acid, an ester, and a different ester. So we've got methyl ethanoate and ethyl methanoate. And then we've got these, we don't name these ones, that's why I've said that. So we've got a hydroxyl group and an aldehyde and hydroxyl and an aldehyde and a ketone and a hydroxyl. And then we've got a double bond. So at some point we need a double bond. So you can't just say the molecule has a double bond. You really need to be specific because is it a CO double bond or is it a C double bond? So whenever you're quoting, if you've got an alkene and it's unsaturated, you can't just write in words, oh, it's got a double bond. You have to write it's got a C double bond C. Yep. So in previous years they have given, as the molecule that you're trying to work out, they have given this kind of combination, double bond and an OH. These are kind of the classic ones, but you might be asked for a ketone or an aldehyde or this double bond. What it would be a property to, so some extra information. This is an acid. Which isomers are soluble in water? So acids would be, as long as they're short, as long as these molecules are short. Esters are not so soluble. They form hydrogen bonds with water, but they're not very soluble. And the longer this chain is, the less soluble they get. So this would be partially, but as soon as you start adding more carbons, it would not be soluble. This would be soluble with the OH, and this would be soluble with OHs both on each side. Lowest flash point, so we need to look at which ones turn into a gas the most easily, so which ones have the least intermolecular bonding. So the esters would probably be having the highest flash point, and the lowest flash point would be the ones that, no, the esters would have the lowest flash point because they would have the weakest bonds. So they would turn into a gas the most easily. Esters tend to have a smell. So yeah, they would be gaseous. All right. Which spectrum? So it's just some practice. It's a yellow page. Which spectrum belongs to which molecule? Note they both have the same general formula. So we've got two molecules, propanoic acid and methyl ethanoate. So pause it, have a look, and work out which one you think belongs to which. Okay, so when you're looking, you can see we've got this broad peak here, which is missing from here. Oops, I think I've got answers on this. This is not much good, is it? It's got the broad OH peak here, and this has got the OH. It's also got the carboxyl, and that's got the carboxyl. It's funny, I'm normally looking at the class when I do this, and I haven't noticed that before. Alright, the top graph is due to the propanoic acid, yes, because there is a broad absorption band between here and here due to the OH group in the acid, which is missing from the second graph, and that must be the ester. And the ester has that. Okay, so we've got used to having OHs here, and our carbonyl here. So now we need to add a bit of complexity to it. This, we can have an amine here, which is all very fine if they give you the formula and it's just got carbons, hydrogens, and nitrogen, then you don't have to worry about an oxygen. That helps, doesn't it? If you've got an amide, though, C double bond oxygen and an NH, then you're kind of wondering what's going on. All right, so if we've got a primary amine, so an amine NH2 that's stuck on the end of a carbon, on the end of a carbon chain, then you've got these twin peaks, and they are the easiest to remember. So if you've got something that looks weird, you know, you've got your CH stretch, and then you've got something going on here, but it's definitely not an alcohol, or it's too short for an alcohol, then and it's got a nitrogen in it, then you've got an amine or an amide. Okay, so primary ones, so when the NH is on the end of a carbon, have the twin peaks, and a secondary one, when you've got the NH between carbons, has a weird, doesn't really look like an alcohol, you know, it's too skinny, too short, and they'd probably have some clue that that's a nitrogen. So it would be a peak due to a primary amine or this is a bit of a problem because we've got this, oh no, that functional group is further down, that's at 1700. Okay, so on the end, got the twin peaks, and if it's in the middle, you've got this could look a bit like an alcohol, but the fact that you've got a nitrogen in the formula would imply that it's an amine. Hopefully they won't give you amines this year. Alright, so these are some others. We've got propanol, it's an alcohol, just for you to be going, oh yes, I remember these. This is further down, closer, so it's a carboxylic acid. This is interesting. Sometimes they try and trick you that you've got a carboxylic acid. You get so used to seeing it written like that if you see something written like this, you go, what is that? It's just a carboxylic acid where that's summarized. And then a ketone, you've got no OH group, no hydroxyl group, and you've just got the carbonyl. Okay.